I'm going to walk you through solubility rules and how to do net ionic equations in this video. A little review here first. Remember, a solution is a type of homogeneous mixture. So it's an evenly distributed mixture here in which one substance is dissolved in another. The solute is the substance that is dissolved, and the solvent is the substance doing the dissolving. So if you look at this picture here, you can see the solute is added, and it's pretty much like the solvent is attacking the solute, and it becomes evenly distributed until you get that homogeneous mixture. All right, so the solute is dissolved by the solvent. And just remember a couple terms here. Insoluble is when something does not dissolve, and soluble is when something does dissolve. We did look at different factors that affect the rate of something dissolving. Remember, we're not talking about something does not dissolve. How can we make it dissolve? No, what we're talking about here is if we have something that dissolves, it's soluble. How can we make it dissolve faster? All right, so think about your cup of coffee. If you want your sugar to dissolve faster, well, stir it up. Agitation makes something dissolve faster. Increase the temperature. Hot coffee is going to dissolve sugar much faster than cold coffee would. Also, if you increase the surface area, all right, crush up the sugar and add it to the coffee, it's going to dissolve much faster than if you used sugar cubes. And then obviously use less. All right, so that one's kind of different. If you use less of the solute, it will dissolve much faster. So those are different things that you can kind of look at that would influence the rate of something dissolving. All right, remember, this is a substance that already dissolves. It's just how can you make it dissolve faster? So that was a nice quick review of some of the terms there involved with solutions. There are two types of aqueous solutions. You have electrolytes and non-electrolytes. Electrolytes are aqueous solutions that form ions. Basically, electrolyte solutions will conduct electric current. You get this when you dissolve ionic substances in water because the ionic substances dissociate. They separate into their ions so the solution can conduct an electric current. So if you put sodium chloride or magnesium chloride in water, that becomes an electrolyte solution because of the dissociation and it can conduct. A non-electrolyte aqueous solution has a substance that's dissolved in it, but it doesn't form ions, so it doesn't conduct. So you want to think about a lot of like polar substances. If you dissolve sugar in water, it dissolves, it forms a solution, but it's not going to conduct an electric current because sugar is covalent and it doesn't dissociate. All right, so the sugar molecules become surrounded by the water, but it's not going to separate into ions, so it's not going to conduct. So that would be a non-electrolyte, and typically you'd expect this for polar substances that dissolve in water that aren't ionic. I just mentioned dissociation, so we want to make sure that we remember what that is. That's when you have an ionic solid dissolving in water and separating into its plus and minus ions. If you remember, the plus and minus kind of get stabilized by the water molecules. That process is called solvation. All right, it's a process that allows these stabilized ions to stay apart and prevent them from coming back together. All right, so basically the solute becomes hydrated, all right, if the solvent here is water. So if you look at this, sodium, remember, is plus, all right, so when you put sodium chloride in water, it separates into Na plus, Cl minus. So water has regions of charge. It has slightly negative regions, slightly positive regions due to polarity. So in order to stabilize the sodium plus, it turns and points all its negative, slightly negative regions toward the sodium plus, so that stabilizes him and he doesn't want to recombine with the Cl minus. But then since chlorine is minus, water turns and points all its slightly positive regions toward the chlorine to stabilize it, so it doesn't want to come back together with the Na plus. If the water evaporates, the Na plus and the Cl minus will find each other again, and you would reform the salt and you would see it form. All right, so this idea of dissociation where an ionic solid is separating into its parts, into its ions, into its plus and minus. What keeps it apart is this process of solvation. There's three different ways to classify solutions. A saturated solution is a solution that has the maximum amount of solute dissolved that it can hold at that temperature. So basically, it can't hold any more. So that's a saturated solution. An unsaturated solution would contain less than the maximum amount of solute that can be dissolved at a particular temperature. So if you had a big cup of coffee and you added a tiny little bit of sugar and dissolved it, obviously that would be an unsaturated solution because it could dissolve a lot more. And then a supersaturated solution is really interesting. Basically, it's kind of like you trick the solution to dissolve more of the solute than it can actually hold. All right. And usually you do this by maybe like warming it up and then more of the solute dissolves and you kind of go past the saturated point. But it's usually very unstable and temporary. Sometimes even the slightest disturbance can cause just a rapid precipitation and a rapid crystallization. All right. So if you had a supersaturated solution, sometimes even a speck of dust hitting that solution can just cause it to rapidly precipitate out. So if you're looking here at the pictures, an unsaturated solution could contain or could keep adding solute. It doesn't have the maximum amount. A saturated solution has the maximum amount of the solute dissolved. So basically, if you started adding more, it would just start piling up on the bottom. And then a supersaturated solution would actually start to form crystals as soon as it's disturbed. So this is a picture here showing a rapid crystallization. You probably had a supersaturated solution that is now rapidly precipitating out. And that's how you make rock candy. Basically, you heat up your sugar water. It dissolves more of the sugar than it can actually hold. And then you have some type of seed, a stick or string. And as it cools, it starts to precipitate out onto the stick or the string. So you definitely need to know these three types of solutions. Knowing when something is soluble or insoluble is very important here. So these solubility rules that you're going to see, you need to know them, okay? If you remember back when we were talking about reactions and double replacement reactions, we said that sometimes double replacement reactions don't happen. It's all based on these solubility rules, okay? So now we're at the point where we need to know these solubility rules so we can determine if a double replacement reaction actually happens. So the first four rules are dealing with when things are soluble with some exceptions here, okay? And maybe it's important to point out here, if something is soluble, okay, that means it's going to be aqueous. So you have to remember this. If something is soluble, that means when you put it in water, it's going to be AQ or aqueous. It's going to dissolve. So if you were writing a reaction, you would label it as AQ in parentheses. Now you need to worry about if things are aqueous or solid here. If something is insoluble, that means it's not going to dissolve in water, so it would stay as a solid. You would see solid in parentheses after the substance. That's very important here. So you can read these rules, but you do need to know them. The first one is talking about salts of ammonium or alkali metal compounds always being soluble. So if you have a compound that has ammonium in it, NH4, automatically you know it's always going to be aqueous or soluble. And same thing for those alkali metals, the far left column. As soon as you see an alkali metal in a compound, you automatically know it's always going to be soluble. Rule 2 says chlorides, bromides, and iodides are usually going to be soluble or aqueous, except when they have silver, mercury, or lead with them. Then they would be insoluble. So if you had silver chloride or lead chloride, that would be insoluble. It would stay as a solid. It would not dissolve in water. Okay, but all the other chlorides, bromides, and iodides would dissolve. Rule 3 is saying that chlorates, so ClO3 compounds, acetates, C2H3O2 compounds, and nitrates, NO3 compounds, are all soluble. Okay, so anytime you see, NO3 in a compound, a nitrate, you automatically know it's going to dissolve, it's going to be aqueous. We call this rule the CANS rule, okay? Chlorates, acetates, nitrates. And then rule 4 is talking about sulfates, so SO4 compounds. So again, you need to know your polyatomics here. These are always going to be soluble, except when you have calcium, strontium, or barium sulfate, or again, the silver, mercury, and lead, which we saw in Rule 2. So if you had silver sulfate or calcium sulfate, that would be a solid. If you tried to put it in water, it would stay as a solid. It would be insoluble, but all the other sulfates are going to be soluble here. So you do need to know these rules and you need to know these exceptions. So the first four here are usually dealing with when things are soluble, with exceptions for insoluble. The last three rules are going to deal with when things are insoluble, with exceptions for soluble here. So Rule 5 says that phosphates, so PO4 compounds, carbonates, CO3 compounds, and sulfides, watch the ending here. So those are things with sulfur in them, okay? They're always going to be insoluble. So they would always be solid. If you put them in water, they're not going to dissolve, except ammonium or alkali metal compounds. Basically, you can't have like a rule like Rule 5 breaking Rule 1. Okay, so if you remember, Rule 1 said that all ammonium and alkali metal compounds are soluble. So these rules work together here. All right, so typically phosphates, carbonates, and sulfides are going to be insoluble, except if you have ammonium with them or one of those alkali metals in the far left column. They're always going to be soluble. Rule 6 says all metallic oxides are insoluble. Basically, what that means is anytime you have a metal with oxygen, all right, they're going to be solids. If you put them in water, they're not going to dissolve. Again, except ammonium and alkali metal compounds, Rule 1, they have to be soluble. And then Rule 7 is dealing with hydroxides, OH compounds. They're typically going to be insoluble as well, except ammonium and alkali metal compounds, again, Rule 1, and it says group 2A from calcium down. Basically, it's the calcium, strontium, and barium again. All right. So in this rule, calcium, strontium, and barium hydroxide would all be soluble. It's kind of different from the sulfate rule. All right. So be careful with these and definitely look these over. So again, now when you look at an example here, you are responsible for including whether or not things are aqueous or solid here based on your solubility rules. So if you look at the first compound here, magnesium nitrate, this follows the CAN's rule. All right, nitrates are always going to be aqueous, so it's labeled as soluble. It would dissolve in water. NaOH is labeled as aqueous because Na, okay, that's Rule 1. It's an alkali metal in the far left column on the table, so it's automatically going to be aqueous. And you could even get this with Rule 7, too. I mean, hydroxides are typically solids, except ammonium and alkali metal compounds, and then calcium, strontium, barium as well. So the rules all work together here. But notice, when this reaction takes place, you get magnesium hydroxide here, and that's going to be a solid. Again, that hydroxide rule says that hydroxides are typically insoluble or solids, except ammonium or alkali metal compounds. Well, magnesium's not ammonium. He's not an alkali metal. He's in the alkaline earth metals. And then it says from calcium down. So calcium, strontium, or barium. He's neither of them. So he follows the rule. He's going to be solid. And then the NaNO3 here, that's labeled as aqueous because of Rule 1. Okay, it's an alkali metal, or the nitrate rule, Rule 3, because it's a nitrate, right? So this double replacement reaction would happen because you got a solid forming. If you didn't get a solid forming, okay, a precipitate forming, the double replacement reaction would not happen. You need to study these rules and you need to know them inside and out. So if we do a little practice here, we just want to label each of these as soluble or insoluble, okay? So you definitely need to look at your solubility rules and figure this out. And eventually you got to get to a point where you know those solubility rules and can just look at something and know if it's soluble or insoluble. Okay, so remember here, if something's soluble, okay, that means it would dissolve in water. You'd see AQ in parentheses after it. If it's insoluble, that means it doesn't dissolve. It stays a solid. So you would see the S in parentheses after it. Okay, so if I were you, I would pause the video, try these, and then come back and see what you got here. All right, so the first one, sodium carbonate, that's going to be soluble, okay, because sodium, all right away, sodium, Na is in the far left column, alkali metal, Rule 1 says it's automatically going to be soluble. When you get to the next one, lead sulfate, this is going to be insoluble, okay, sulfates are typically soluble, all right, but then not calcium, strontium, barium sulfate, or silver, mercury, or lead sulfate. All right, so it follows the rules here. The next one, barium nitrate, is going to be soluble. All right, nitrate, right? The cans rule, nitrates are always automatically going to be soluble or aqueous. Ammonium phosphate, automatically going to be soluble. Ammonium compounds, rule 1, are always soluble, always dissolve in water. And then cobalt 2 hydroxide here is going to be insoluble. All right, hydroxides are typically solids, except ammonium or alkali metals. Well, cobalt's not ammonium. It's not an alkali metal. It's a transition metal. Or calcium, strontium, or barium. He's neither of those, so he follows the rule. He would be insoluble. So definitely know these solubility rules. Now we're going to see how you can use these solubility rules to do something called net ionic equation. Okay, net ionic equations are when you're only showing the ions that are directly involved in the chemical reaction. So you're kind of getting rid of any of the extra stuff here. You would only do a net ionic equation if you're told to do a net ionic equation. Okay, so you wouldn't do this all the time. It basically takes equation writing and goes a little bit further with these solubility rules. So before we do this, there's something here called spectator ions that you need to be familiar with. All right, these are ions that would be on both sides of the equation, so they cancel out. All right, because they're the same on both sides. They're not directly involved in the overall reaction, so they cancel out. So when we're doing one of these examples, we'll look at some of these spectator ions. So here's basic steps for writing a net ionic equation. The first thing, you need the balanced equation. So you know you need to be good with writing and balancing equations, maybe predicting products here. You need to still do that, all right? But then you would rewrite the equation showing the ions that form in solution for anybody that's soluble. So you will need to use solubility rules here in your balanced equation. All right, anybody who's soluble or aqueous is going to have to turn into their ions, and we'll see what that looks like. All right, any spectator ions then would cancel out on both sides. If all of them cancel, you actually have no reaction taking place. The reaction itself would not happen. All right, but you still have to show everything canceling out. And then the last thing you do is just rewrite what's left, and you'll have your net ionic equation. Again, you're only doing this if it says to do the net ionic equation. So let's just jump in and do an example here. So for this reaction, you can see it's completely written and balanced already, and all of the solubilities are already in there. So don't think that every net ionic equation is going to be like that. You might have to go through and write the reactants and predict the products and then balance it, and then knowing your solubility rules here to be able to do the aqueous or solid. But if you look here, you can see that we are using those solubility rules. So for lead 2 nitrate, nitrates are always aqueous. Potassium iodide, potassium is an alkali metal, so it's always aqueous here or soluble. But this lead 2 iodide is listed as solid because remember, chlorides, bromides, and iodides are usually soluble or aqueous, except silver, mercury, or lead. Okay, so that's going to be a solid. And then for the last one here, it's listed as aqueous or soluble because you have either the alkali metal rule 1 or the nitrate from rule 3. All right, so that's already done for us. All right, so we wrote the equation, we balanced it, we indicated the solubility. So because we're doing a net ionic equation, we got to go a little bit further here now. Okay, so what we're going to do is, once you have your equation written and balanced, it's important to make sure it's balanced here, with your solubility, you now look at every compound individually. So for this first one, the lead 2 nitrate, I see that's aqueous. Anybody who's aqueous, what that means is if you put it in water, it's going to rip apart into its ions. Remember, all right, ionic compounds here are going to dissociate in water. So if lead 2 nitrate in water, it's not actually lead 2 nitrate. It's going to rip apart into its ions. Remember, ions have charges. So when you put lead 2 nitrate in water, it's going to turn into Pb2 plus, because that's the first ion here. That's going to be your cation, plus 2 of the NO3 minuses. Very important to realize here that according to this formula, there's got to be 2 of the NO3 minuses for every 1 of the Pb2 plus. Okay, so the reason we're doing that is because it's aqueous. When you put it in water, it's going to dissociate and rip apart into its ions. All right, Next one, Ki is also aqueous, so it's going to rip apart into its plus and minus. So it's going to turn into 2K plus 2I minus. Notice when you balance the equation and you put your coefficient in front, that carries through for both of these here. Then when you get to your PbI2, it's listed as solid. So when you put that in water, it does not dissociate. It does not dissolve. So it stays as PbI2, and you must include the solid to indicate that that's why it's not dissociating. All right. And then we have the 2KNO3. It's aqueous, so it's going to rip apart into its ions. 2K plus 2NO3 minus here. Okay, so you ripped apart all of your aqueous substances and turned them into their ions. The solid stays together. Now we're looking for spectator ions. All right, those that are the same on both sides of the equation that are basically not important here for the overall net ionic equation. So I can immediately see that K plus is the same on both sides. There's 2K plus on both sides, so he's gone. That would be a spectator. All right, and then I can also see that there's 2NO3 minus here on both sides. So that's gone. That's a spectator. If I asked you, if I gave you this reaction and I said, what are the spectator ions? You would tell me K plus and NO3 minus. Okay, so the spectator ions are gone. So now you're ready to write what's left. So we got Pb2 plus 2I minus going to PbI2 solid. This would be your final answer here. All right, and that would be your net ionic equation for this. Typically, it's already balanced. If you balanced it, sometimes you might have to simplify it, so you just got to watch. But this would be your answer for this problem, and you do need to indicate the solid here in parentheses because that's what's saying why that didn't dissociate. So that's a pretty basic example of a net ionic equation. We're going to try another example here. So for this one, they gave us the reactants, and they told us whether they're aqueous or solid. So they went through and used the solubility rules. So we have to predict the products here. All right, so the first thing I have to do is I have to look at the reactants and figure out what type of reaction this is going to be. So I see that the first substance is a compound. The second substance is a compound. So this is going to be a double replacement reaction. Okay, so that tells me, all right, what my products are going to be here. The K is going to essentially stay. Its new friend is going to be the Cl. When you do symbols, charges, crisscross, it's going to be KCl. And then you do have to indicate if it's aqueous or solid here. So when you do this, all right, you'll quickly see that it's going to be aqueous because of rule 1. Potassium is an alkali metal, far left column, so always aqueous. Then the calcium's new friend is going to be the CO3. So when you do symbols, charges, crisscross, the 2 plus on the Ca, the 2 minus on the CO3 cancel. So it's just going to be CaCO3, and that's going to be solid, all right? Carbonates here are typically solids. Remember, phosphates, carbonates, and sulfides are typically solids or insoluble, except ammonium or alkali metal compounds. Calcium is not ammonium, and it's not an alkali metal, so it follows the rules, okay? So now you have your products predicted here. You have to go through and balance. So it looks like I'm going to need a 2 in front of the KCl, and then it looks like everything else is balanced here. All right, so now I'm ready to go through and work on the net ionic part here. Again, you would only do this because it's telling you to do a net ionic equation. So anybody who's aqueous would dissociate in water. These are ionic compounds, so they have to rip apart into their ions. So I see that the K2CO3 is aqueous, rips apart. It's going to be 2K plus CO3, 2 minus here. All right, aqueous for the CaCl2. So you're going to have Ca2 plus 2Cl minus going to, okay, KCl is aqueous. So we got 2K plus 2Cl minus here. Remember, anybody who's aqueous rips apart into their plus and minus ions. Pay attention to the amounts. But the CaCO3 is solid, so it's going to stay as a solid. It's not going to rip apart. All right, so now we're looking for any spectators. I see the K plus is the same on both sides, so he's gone. The Cl minus are the same on both sides, so that one's gone. And then I write what's left. So I have CO3, 2 minus, plus Ca2 plus, going to CaCO3 solid. All right, so that would be the net ionic equation for this particular reaction. It's only showing the substances that are involved in the actual reaction. So there's one more example here we're going to try. All right, again, we were given the reactants already with the solubility indicated. Don't always count on that happening. You might have to do your symbols, charges, crisscross to write out the reactants and then predict what forms. But again, we have to figure out what type of reaction this is going to be. We have a compound reacting with a compound. So that's going to be double replacement here. All right, so that tells me that, they're going to have two things switching. So barium's going to get a new friend on the product side. So when the barium joins up with the chlorine and you do symbols, charges, crisscross, it's going to be BaCl2, and that's going to be aqueous. Chlorides are typically aqueous or soluble, except silver, mercury, or lead. Well, barium's neither of those. Plus, we got Na joining up with the NO3. When you symbols, charges, crisscross, they're both 1 plus 1 minus. So it's going to be NaNO3, and that's going to be aqueous here. All right, because of rule 1, alkali metal always aqueous, or the nitrates always being aqueous. All right, so don't forget we have to balance this. Some people get so excited because, they're doing the problem that they forget to balance. Sometimes I do that, so you have to be careful. Looks like we need a 2 in front of the NaCl, and then a 2 in front of the NaNO3, and then that should make it balanced here. All right, so anybody who's aqueous now, you got to rip apart into their ions. So it looks like I got Ba2 plus 2NO3 minus plus 2Na plus 2Cl minus going to Ba2 plus 2Cl minus plus 2Na plus 2NO3 minus. Okay, they were all aqueous here, so anybody who's aqueous rips apart into their ions. So now you're looking for spectators, anybody who's the same on both sides. Well, I see 2Na plus on both sides. I see 2NO3 minus on both sides. I see 2Cl minus on both sides. And I see a Ba2 plus on both sides. So if you notice, everything canceled out. So this would be listed as a no reaction. RXN stands for no reaction. And you do show your work, show everything canceling here. But again, the reason why this didn't happen is because you didn't get the solid forming. You didn't get a precipitate in your products here. All right, so you should immediately know that this would not be a reaction. If you actually mix these substances, this double replacement reaction would not happen.